Thanks for coming. Hope you had a good break yesterday afternoon. So yeah, we are sort of in the middle, or we did the kind of intuitive path towards a solution to this rainbow cycle problem. So remember, what we're trying to do is we have a graph which has degree log squared times log n squared, and it's properly edge colored, and we're looking for a rainbow cycle inside of it. And last time we set up a lot of the stage, and today we just need to kind of finish off the plan that we set up last time. But let me quickly just remind you through it, and I've kind of written it up in a maybe more concise form, because last time I was trying to explain more intuition and why certain things don't work, and then the setup maybe looked a little bit confusing because of it. So we pass into an expander. So as I said last time, I'll just assume our initial graph is an expander not to relabel everything. So that's our robust sublinear expander. So I've written here what that means to remind you. It will show up a bit later. And it will get slightly modified as we go, because we'll lose parts of it as we tweak things. Then the key object that we're chasing are these rainbow neighborhoods. And this is just the set of vertices that you can reach by a rainbow path, starting from V, using the colors from some prescribed set. And they should have length at most L, which is also a parameter. Right, so these are our usual neighborhoods that we grow in the diameter bound, except here we want them to be rainbow, because we're not looking for arbitrary paths, but rainbow paths. Right, so this is nothing too scary or new. So the radius that we will eventually take of these neighborhoods is going to be 1,000 log n log log n, and this is just chosen so I don't need to be careful about constants. You can be much more precise. And really the key claim that I explained we want to get last time is that we want to show that with probability at least a half, if you do take this radius r neighborhood around the vertex, you reach more than half of the vertices with probability more than half. And then the trick was that, well, if you have this for some set, then its complement is also distributed as C1/2. So you can split your colors into two, and you can ensure that this is true from some vertex V for both this and it's for both some set and its complement. And then you use that, and now we do our standard diameter argument. Well, slightly different because we're expanding from the same vertex and not two different ones. And then eventually we found some vertex that they intersect in. We reached it by a rainbow path from the left. And why am I having a blue here? Yes, let's make a green longer. Yes. Yellow was the one that's missing. OK. So you reach this common vertex in two ways, with a rainbow path here from C prime and with a rainbow path from its complement. So that means when you put these together, you get a rainbow walk. And this rainbow walk then contains a rainbow cycle, and we're done. So when we prove this claim, we are happy. So we want to kind of show that it grows correctly, and that it essentially grows even if we were just expanding usual neighborhood instead of the rainbow ones. And this is what robustness will really give us. So main idea to prove this, or the proof that we are doing at least, is based on sprinkling. So this is a very powerful probabilistic trick that pops up in lots of different places. And the idea is, instead of showing this whole thing immediately, we are going to show it in stages. And these stages, we are going to have R stages. So our probability should be roughly 1/2 times R. I put a 4 so that I don't need to be careful about that computation, so that the union of all of these random sets we take will be distributed as some CP prime with P prime less than half, so it lives inside of that set. Right, so each of these things are mutually independent random subsets of our sets of colors chosen with probability P. So roughly 1/log if you look there, log if you look what radius is. And what we care at stage I is we allow ourselves to use the first I stages, first I sets of colors, and we reveal what the set is. And at this point, all of the remaining sets are still completely random. We did not influence them at all. So we want to use the next one and say that when we reveal the next one with kind of good enough probability, we will grow as if we just expanded in the usual way. So that's the plan. So again, the key claim is implied if we show that for this, like when you reveal all of these sets, you reach with probability more than half, more than n plus 1. Over 2, that's more or less restatement of key claim. Just this thing has slightly lower probability than 1/2, but it's dominated. And now the real main goal is written here, which is that these rainbow neighborhoods grow correctly as we go out. So I'll be calling them UI, so just so I don't write this whole expression the whole time, and because these are going to be the sets that we expand by our robust sublinear expander property. And then the goal is that the I plus first is bigger by 1 plus epsilon roughly than the ith one, with probability that now needs to be a bit closer to 1 because we will do this multiple times, right? So we have R stages, so we need this to survive a union bound over R things, which is why that was picked that way. And in particular, we will prove this for any outcome of our first I samples. So that gives you some rainbow neighborhood that we got there. And now we are interested in proving that this is then true for the I plus first, right? So the whole randomness here, the only randomness that exists, comes from the I plus first one, which means we sample colors with this probability P. And using only those sampled edges, I want to show that I'll still get that many new vertices. Okay, so that was the plan that we outlined last time. And that, so what remains to be done is to prove this lemma. Very good. So we also had the notion of blocked edges. So we use them kind of to illustrate that we can grow these rainbow neighborhoods if we just use the whole set of colors. They also show up here, and they're again the same. So I wrote the definition last time. I'll not write it because it's long, but really these blocked edges were, if you remember, when we have this rainbow neighborhood of radius I, any edge that, if you use it, there is no rainbow path that will bring you to the origin, right, together with this thing. So in particular, this edge is not a witness that if we sample that edge, then this vertex goes into UI plus 1. Right, so let me draw some colors. Yes, this, and then suppose that this one is orange, then this is a blocked edge, and suppose that this is the only rainbow path, or the one that we fixed, you can choose how you want to think about it. So this is a blocked edge. And it's verbose to write what this thing, as you've seen last time, but I hope it's clear what I mean by the blocked edges. So the ones that are not useful to us. Even if they get sampled, they don't give us anything new. Everyone happy with that? Okay. So another thing that we observed last time is, so if we write F to be the set of blocked edges, then we get a nice upper bound on it. And in particular, F has size at most I times, because the length of this rainbow path is I. So at this vertex, you have at most I edges that get blocked. And you have in total UI many vertices there. So this is at most I times the size of UI. And let me write now that U is just the size of UI. So this is the set that we will want to expand and show that it grows. And let me also set up our usual parametrization. So U is n to the 1 minus epsilon, so that these epsilons make sense. So note that epsilon is always going to be at least 1 over log. So this is something we said about these robust expanders, because we never want to expand more than a half. So technically, I should probably put a 2 here, because I have that plus 1 there, but let me try not to do that, and hopefully no one objects. Right, so that's our whole setup. And now in particular for this F, we know that size of F is at most, so I will always be at most R. And then we have U here, and this is supposed to be less than epsilon times degree times U over, let's say, 8. Right? Why is this true? So D is log squared. This is always at least 1 over log. And this is log. I'm ignoring log-logs because we get them extra here. OK? Make sense? So the point is, this is always less than what we are allowed to forbid in the expansion of our set U by a half. So in particular, even if you forbid F, you are even still allowed to forbid another that many edges and still get expansion. OK? So let me get rid of this. And let me here put, OK, maybe this one is in the way. Let's move it there. And current expansion, and I will be updating this here. So let's say this board is for tracking all the numbers. So current expansion is can delete, so in G minus F, can delete up to epsilon du over 8 edges. And we still get epsilon over 4 times u new vertices. Right? So when we delete F, it has size at most half of that. So that means you can still choose arbitrarily another epsilon d over 8, and you get that property. OK? So these numbers will update now as we go through the argument a few more times, because we will kind of clean the graph, change the graph, look at what we're doing, and we'll be slowly losing this property as we do that. But it's going to survive up to loss of constants throughout the stage. Very good. So now the point of these F and the point of forbidding them is that in G minus F, any edge now that you get, so in G minus F, if we have our UI, any edge that still goes out, if it gets sampled, this vertex goes into UI plus 1. Right? So we now no longer need to worry about these strange edges that don't help us. There was few of them. They don't impact our expansion. Everyone else is good for us. OK? So now really the question is, you have a set of size U. It has this level of expansion. And if I sample all of the edges going out of it with probability P, which exists somewhere there, so P is 1 over 4R, then you get at least epsilon over 128 times U new vertices. Right? So this is now just a statement about a bipartite graph, which has a certain level of expansion. We are sampling its edges. And I want to claim that with a sensible probability, enough vertices survive that sampling. So it completely reduces to this. In a paper, we have a nice kind of lemma that generalizes what I'm going to do now, but I don't want to state it because it, again, gets long to specify everything that's going on. But, and also, just a caveat, I was saying something. You're not sampling edges, you're sampling colors. Right? That's the key issue. If we were sampling edges, we would essentially be done immediately now. Colors are a bit problematic because they have dependencies. So for edges, you can do a Zuma here, and you're happy, for example. If for colors, you can also do a Zuma, and you're happy if U is small, but not happy if U is big. So because, anyway, let me not explain why a Zuma doesn't work, but you can try convincing yourself if you don't believe me. Very good. So now let me define this bipartite graph just to get rid of all of our other setting and setup. Right, so let H equals A and B, E be a bipartite graph, bipartite induced subgraph, and I mean by induced that you only take the edges between A and B, not inside of the pieces, but anyway, of G. with A is just our UI, okay, and B is everything else. Right, so this is precisely what I tried to kind of draw there. So we only care about the edges that go from UI outside. And we are just calling this A and calling this B, because they will update dynamically now through the argument as we do some cleanup to actually get this to work. Okay, and so now goal is when sampling colors, with probability P, we want at least epsilon u over 128 vertices of B to survive. And survive means still have a neighbor in A. Yeah?
Is this supposed to be a subgraph of G or of G minus F?
G minus F, thank you. We deleted F. Yeah, perfect. Thank you. And of course, this we want with the probability because this sampling is a random thing. And what we want from this probability is that whatever we wanted there, it's really just a restatement of the statement that we had somewhere there. So that should be 1 minus 1 over 2r. Good. So now we have just a kind of clean graph theoretic bipartite graph sampling probabilistic combinatorics problem. So let me still do it because it's a typical type of problem that you see when working with these things. And the kind of, when you try, the first thing you try for this is Azuma. And it tends to fail because you kind of have too low expectation compared to Lipschitzness. So you kind of need to do some acrobatics to get these things to work. It's not, you'll see that it's actually even simpler than Azuma, what I'm going to do, but it's good to see it, I think, once. Very good. Any questions at this point? Great. So first case, there is at least epsilon u over 8 vertices in B with degree, and all my degrees refer to H now, so without F in particular. H bigger or equal than D. Okay, so if that happens, then I claim that each of these vertices has such a good chance of getting sampled because getting one of its edges sampled, that we can just do a union bound and we'll get that they all survive. Right? So what we're saying here is you have a vertex that has a degree D going here. Because we are in a properly edge-colored graph, all of these colors are different. Right? So the chance that it actually, the chance that that vertex survives our sampling procedure is just 1 minus p, whatever. It's some binomial thing. So each of them, such vertex, survives with probability at least, or actually it's exactly, well, okay, probability at least because it might have more than D. So it's 1 minus p to the power D. Right, so this is the chance that we sample none of the colors that connect it to UI. And this is the chance that then we do sample at least one. So this is at least 1 minus e to the minus pd. So this is the standard estimate on 1 minus p. And p and d are, so d is some log squared, and this is 1 over log. So this will have a log here, so that will be a polynomial thing. Okay, so this is at least 1 minus n to the minus squared, or 2, or so you can do it better if you wish. Maybe let me put 3, I think, just so I have some space to waste. Good. So that means by union bound, all these vertices survive. With probability at least 1 minus n to the minus 2. Right? We have at most n such vertices, actually epsilon u over 8, but you don't really have control how big u is. It might be linear, so you might as well do n there. So I guess 2 there was fine. And then you just get 1 over n. And then you say that this is at least 1 minus 1 over, what did we want? 1 over 2r. Right, this is a log size thing. This is a polynomial size thing, so we're happy. So that gives us that in this case we're done, right? With that probability, all of these at least epsilon u over 8 vertices survived. So quite even more than what we have here. Make sense? Okay, so if we have less than that many vertices with degree bigger than d, then we will just delete them. Right? So this is what I meant that our graph is going to update. So now we are going to look at this B and delete this small number of vertices from B. So in the notes, I'm writing that this is now B prime, and I'm being more careful, but here I will not, because we'll get to B prime 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 at some point. And so just keep in mind that A and B are updating dynamically. So when I say I delete things, I mean the new B is still, you have an algorithm which redefined what B is, if you wish. But I think, don't worry too much about it. It should not matter too much. So second case, we have less than epsilon u over 8 such vertices. So now delete them. So from B, right? And what happens to our expansion strength? So we deleted epsilon u over 8 vertices. So still, no matter what, like when you expand this u, no matter what edges you pick, you got double that many vertices. So we only lost half there by deleting this, right? So this now becomes 8. Right? In our new H, this is the rate of expansion we have. And again, I'm not going to be copying everything, but just kind of doing this bit. But makes sense? Good. And what did we gain? We gained the max degree in the new graph on the right. So delta max, delta right is what I meant, is now at most d. Good. So now what really our next goal is to just show that when we sample these colors, the number of edges that we get is sort of what it should be. And what it should be is we get at least this many edges, right? Because if you don't have that many edges, you can just delete all of them and you get no expansion. So the number of edges in our bipartite graph is at least that. We are sampling with probability p. So in expectation, the total number of edges is p epsilon d times u over some constant. And I want that with some smaller constant, that happens with kind of 1 minus whatever probability that we have there. Right? So that's our goal. If we get that, then this condition ensures we get enough vertices on the right, because each of them is also with high probability going to have at most PD sampled edges next to them. So if you divide that by PD, well, times P and divide by PD, you get epsilon d over a constant, and you get enough vertices on the right. So that's the strategy we're doing. So the main thing to show is that we do get the correct number of edges in between these two sets. Okay? Very good. So we need another step of cleanup in order for this to work. So remove any vertex from A with less than epsilon d over 16 edges, with degree less. Okay, so what did that do to us? So we just deleted some vertices from A. So that means kind of we deleted some edges from here. So whenever we think about the expansion here, we will always include all their edges. There is at most epsilon d over 16 times u, right? Because there's u vertices in A at most. So we kill at most half of what we have here. So the expansion on the new graph just lost another half here. Make sense? Okay. So what we got by this is that we have a minimum degree on the left of epsilon d over 16. And maximum degree on the right. Okay? Good. So now, maybe I go there. Now we are interested in the vertices on the right and which of them survive. So let's introduce random variables which just indicate the random variables whether they survive or not. Actually, I want to do it from the left. So let me trust my notes. So let x1, and yeah, I should do it from the left. So note that we no longer have u vertices. We have some maybe smaller because we deleted some a, but then we still have the expansion which is controlling our size of everything, left and right. So let these be random variables, counting the number of sampled edges incident to a vertex I in A. Right, so I go through everyone who is still in A. I look at all the edges there, and I introduce a random variable which tells me how many should survive. Right, so this is again a binomial random variable because it's a properly edge-colored graph. You have distinct colors, so we're sampling colors, but we don't care because they're all distinct incident to vertex. So these are again binomial. So let me also let di be the degree. Vertex I in A. So I'm thinking of A as being 1 up to u prime, so that I don't need to write some notation extra there. So we know that, I forgot to actually define the thing. So what we know from the minimum degree thing is that it's always at least that. Right, so now this xi is just distributed as a binomial where we have di elements and we sample them with probability p. So that means by Chernoff that probability that xi is less than p di over 2 is less than e to the minus p di over 8, which is less than because we have this lower bound on the degree. This is why we did that, right? You can put epsilon d over 16 here. So this is at most e to the minus p epsilon d over 128, right? 8 and 16. Yes?
So just to follow, so these xi are distributed like binomial because we're sampling colors, but the coloring is proper.
Yes, and these are just incident to a single vertex.
Yeah, okay, so they're not independent among themselves, like you.
So yeah, so these variables are not independent at all. So we need to be careful about that. That's the whole problem. But like individually, they are just individual binomials.
Thank you.
Yeah, thanks. Now, please do ask clarifications, especially good ones like this. So let me copy here what we know. I think this one we maybe no longer need, but let it survive. Yeah, yeah. Of course.
From before, so we deleted the vertices of high degree C, right?
Yes.
How did we know that that didn't just kill all of our edges? Or sorry, up or down through the number of edges we deleted?
So there, if you had enough of these vertices, so this now got erased, but there was this first case and second case. If you had enough of them, then just by union bound, each of them survives.
Right. So you have a few of them.
So you have a few of them, and if you have a few of them, then you know that whatever you delete here, you need to get double as many vertices in the expansion, because we deleted less than half of what was our expansion, vertex expansion before. So that means even after that deletion, so think of it with the vertices back in, do the expansion, you get at least double as many vertices that live there. So that means that, like, even with the deleted edges and deleted vertices, you still get this many new vertices that expand. Right, so this was double. That's the problem of updating this dynamically, but it would take me forever to copy it 5 times that I'm changing it. But it's a very good question, and please do ask. Make sense? So the main thing was just that you have extra space, you have double as many guaranteed extra vertices compared to what we deleted. So that means that you still get a nice expansion, even though we deleted some vertices on the right. Whatever you delete, and then like the size and everything is just controlled from the expansion side of the world. Very good, very good. Right, so let me call I bad if this happens. Just so I don't copy this expression a few times that it's going to show up now. So, as you precisely pointed out, these are not independent, so we need to be careful. So let's look at their expectation. That doesn't care about independence. So expectation of, and let's look at the expectation of the bad ones, right? So the bad ones are the ones that didn't sample correctly for us. So we would like to say that there is few of them so that we can conclude that there is lots of them that sampled correctly, which gives us then enough edges, which was our goal. So expectation of the sum I is bad of degree of I is just equal by the standard linearity of expectation to the sum of probability that I is bad times di. Yes? So definition of, yes, so this is, so technically how you're writing this is there is an indicator variable here that I is bad, which multiplies di, and then when you take the expectation of the indicator, you get the probability. I skipped a step, thank you. Good? Yeah. So we have an upper bound on this. This is what we did there, right? So this is at most sum of I is bad. No, sum of everything, sorry. Our current A, di times e to the whatever is written there, p epsilon d or 128. Right? And really what we want to compare is this to that. Right? Because we want to say that this is smaller than this. So this is the total number of edges we get sampled. Well, not sampled, we need to multiply it by p to get the expectation of that. But then this is the total number of things that ended up being bad. So what we'll do is we'll just use Markov's inequality. Right? So what can you do when you have a bunch of variables which are not independent and which don't cooperate and are not Lipschitz enough for Azuma? Well, more or less the last resort is Markov. That works always. So probability, so because we don't want expectation there, we want probability, right? We need to show that the number of edges we get is with it's with height probability and not just in expectation. Right? So this is why we're doing all of this. Expectation is not good enough for us. Right, so probability that the sum of I is bad of di is bigger than a half of the total sum is by Markov's inequality at most the expectation of the thing on the left, so sum of I is bad, di, divided by what we want to lower bound, right? So this is 1/2 times sum of I in A, di. Right, so and this is Markov's inequality. Okay, so, and what's the point here? Well, we got this same expression in that upper bound on the expectation as we have here, so they will cancel. So what we get is that this is at most twice e to the minus p epsilon d over 128. Okay. So we're almost done. We have 2 more lines, 3 maybe. So with probability, and this one is, so p is 1 over log, log, epsilon is 1 over log, and d is log squared, log squared. So log survives here. So here is why I have this extra log. And you actually can do all of this business a bit more carefully and not pay that log. That's your exercise for later. But what we're getting here is that you can get a log in the exponent, so you can get a polylog bound here on that. No matter what p epsilon and what epsilon is at any stage, it's always at least 1 over log, right? So with probability at least 1 minus 1 over log cubed, and we have, and I delete the definition of bad, which is bad. And we have where it is, sum of I bad, di is less or equal than 1/2 of sum of i's in A, di, which means that the sum of not bad ones is at least 1/2. Right, and if you remember, not bad meant that we sampled at least p times di over 2 edges. So that means we sampled at least sum of p di over 2. So this is I not bad. Just let me see. I need to put another inequality if I want that, and then it doesn't fit. Right? Because the total number of edges we got from these not bad ones is p over 2 times that, so you get, okay, 4. Very good. That's what happens when you skip steps. Make sense? So this just went back to the definition of bad. Any questions about any of this? And now we're done because this really is like a p fraction of the total number of edges that we have. And this is what we wanted. So it means at least p over 4 times whatever our edge expansion condition is still at this point. So that's epsilon times d times u over 16. Right? We still have at least that many edges at this point. So the sum of di's is at least that. And this was precisely this form that we wanted to get. So p epsilon du over 16. And we got it with high probability and with kind of sufficiently high probability to beat r, which is just a single log. And this is log cubed. OK, so one final line that completes everything is just to remember this max degree condition, because we want a number of vertices on the right and not just the number of edges in total. But because we have a max degree condition on the right, and again, the degrees are binomial, so they are highly concentrated. So with probability, I need this to hold with probability 1 minus 1 over log n, because how this sprinkling process works is that in each step you have a certain proportion of events that are going to fail. And this is what, where we just give up, this is not good for us. And the sum of all of these proportions needs to be less than a half that we get in the end. Yes, because we have R stages, so they need to survive R stages of sampling. So if you remember, at some point I said I want 1 minus 1 over R, and R is a log, 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 or something like that. So this is better, but what we want. But sprinkling, like this is how many stages we have, how many sets we will, like, in quotation marks, expand over the process. Very good question. Right, so with probability this, max degree on the right, after sampling, is at most 2 PD. Right, so this is another Chernoff, another independence on the right, etc. So this again happens with polynomial probability, so much better than what anything else we're chasing. And now we're done, because if you have this many edges, and every vertex on the right has that many, that max degree, then you get like P and D cancel, and you get epsilon U over 16 divided by that. So that's 32, and I don't know why I got something better than what I wrote there, but sounds suspicious, but hopefully not. So if both outcomes occur, it's not 16, it's 64, right? Yeah. I should trust my notes more than myself. Comes occur, we have, and then we get the number I stated. Comes occur, we have at least P epsilon D U over 64 divided by 2 PD. So P and D cancel, and you get epsilon U over 128 vertices surviving on the right. And they're actually thriving. They have lots of edges back, but we don't need it here. Very good. So that's the end of the proof. Took quite a bit longer than I expected, but yeah, so especially this like a little bit fiddly cleaning type things. But it's something that happens quite a few times when you're working with this type of things. I think it's good to show, even though it's kind of pretty natural that given the expectation and what you have a control here over, this should work out. Any questions about any of this? Yes? I think the problem is a little bit with kind of how you reveal these things, and that I want to later do it for the complement of the colors that you do. So like it needs to be in total a C1 half, like the distribution. So I need to keep, so I mean, I'm pretty sure that you can get a way around maybe that if you carefully define what your events are. But I think it's not like, it's fighting a log-log. And if you want to fight that log-log, you can put some sort of like deteriorating function on the, and you will not gain the other log-log that way just because diameter is log-log-log. So you will never kind of save that. So I mean, maybe on log squared you can save it, but not on log-log-log. But again, it's a good suggestion. I'm pretty sure that if you define it carefully, you can do it, but I'd rather leave it as a kind of standard sprinkling, and we show what happens after each I steps, and then we want that accumulated probabilities don't go badly. We can chat about it later. Yes? Yeah. Yes, so I thought I would say tiny amount of like how you get rid of the other log. But so there were multiple steps here if you kind of chase where kind of this other log would have killed us. So you need to be really, like this is happening in the proof of log, 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 essentially everything that I said somewhere. So you just need to do everything much more carefully. You need to, like, and there is, like, on the technical side, there is quite a lot of things that, like, you need to very carefully do. But really kind of the key idea that, that lets you save this other log, in my opinion at least, came from this removal of edges, if you remember, and the blocking edges. So the main issue that I always viewed as the main issues, kind of the rest is also hard, but like it's more technical, so it kind of seems okay. If you try hard, you probably, if it's true, you'll be able to do it. But what was the main issue was that when you have this set UI that we're expanding and you have these blocked edges, and if you had degree, which is just log, 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 and you reach the stage where epsilon is 1 over log, now you can only tolerate log, log vertices at every vertex here as bad. This is the strength of the expansion you are getting at this level. And these are big sets. Here it's very hard to save and do better on these expansion type things. So really what the key idea to get rid of this one log here was that, okay, so it might happen that, so look at this U and look at all the edges that go out. And we kind of, so what can happen is you have too many blocked edges here. If that happens, I claim you now need to go back to the definition of blocked and be very careful in the sense that for this point, all the rainbow paths that go from this point back should use this red color, right? Otherwise, this would not be a blocked edge. So this is slightly stronger than what we were doing, and it's crucial here. And now what's the point? Well, how did we get to this set UI? Well, we just sampled something randomly in the previous step. And this red color had a pretty decent chance of being sampled, I mean, same as everyone else, in one of these previous steps. And if that happens, then this vertex did not belong to UI minus 1. So what we're proving is you will not grow in a single step necessarily, but you will grow in 2 steps. And this now needs a very delicate random process definition, which allows you to go back and forth and argue that kind of you are getting exactly the same pictures going forwards and backwards depending on what happens. And here there is another key lemma from the expanders that let you kind of partition into edges that kind of are good forwards and edges that are good for backwards. And so there is, but really this observation that you have this color appearing on every path back, and because we're building this randomly, then sort of the chance that this got added in the previous step is sort of the same as what we had in this argument for the new vertex to get added. So in expectation, you grow at the same rate, maybe not from this step to this step, but then from this step to this step. But yeah, it's like a 20-page extra of work. So yeah. Very good. Any other questions? So, and I don't know how to do those 20 pages, so easier than that. So, so one question, one exercise for you is kind of redo this argument and show that you can find rainbow subdivisions of any constant order. I'll not write it because it takes longer. It will be in the notes. But if you remember this topological cliques we did without colors, so actually there is also a parallel problem to this, where you want to, instead of a rainbow cycle, you want to find a rainbow subdivision of kt, where t is a constant. And so it's a very good exercise to kind of make sure you understood what was happening here and run it. And actually, that one is open whether you can get rid of the other log. So if you want an open problem to attack after that, that's also there. I thought about 5 times so far I know how to do it, and every time I did something wrong. So it's be careful about it, but it's a very nice open problem. And actually, I think the proof I showed you here would give you a slightly better log-log than what is known. Actually, Oliver, can you do rainbow subdivisions with homomorphism counting? Yeah, I also never tried, but occurred to me now. Anyway, yeah. So the current published best bound has more polylog logs than here. So if you want to get better polylog logs, you can do this. And you should be able to do it for sure with just a single log. Very good. So that's the rainbow cycle story. So for the last one lecture and 10 minutes, we're going to talk about decompositions. So let me at least state the decomposition lemma. And so I want to illustrate what I showed you so far. Is the way of using these expanders where you pass into an expander and then find something there. So now I want to show you an application to a problem which clearly does not have that structure. And the key difference is that we are not going to just find one expander, we're going to tile the whole graph with them in a certain way. Okay? And then put them all together. So I want to change the definition of expansion a little bit because it will be too messy if you keep working with that. And I don't actually know how to tile into these strong expanders, decompose into these strong expanders. So, I mean, I know if you give me a bit more slack in the vertices, I'll explain a bit later, but the main issue is in the strength that I want there, I can only get 1 over log squared an expansion for big sets. And then this kind of distinction of how well you expand at which point, which you can get in this lemma as well, stops being so relevant because you will lose some polylog anyway. So the decomposition lemma is a bit weaker than pass to expander lemma as far as I know. And I never managed to make the argument in which you take this one, take it out, and keep doing that work. But yeah. And anyway, let me state what the expansion I want, and then maybe say something more. So G is an epsilon S robust expander. And technically sublinear if you want, but since I'm putting epsilon, I'll just say expander. Also, it makes it different than the definition we had there, which is good. If for every subset of the vertices, which is not bigger than, say, 2/3, and every subset of edges, which is not bigger than an S factor of U, we get this expansion when we forbid this edges F or by an epsilon factor. Okay, so it's the same expansion as we had kind of before, except we no longer adjust epsilon based on the size of the set we expand. So for example, that graph is always a d over log n. It's 1 over log n times, okay, 1 over 4 log n and d over 4 log n robust expander. So this just takes the worst case of what happens here and does not play with smaller sets. And you can actually refine the lemma that I'm going to tell you to get something better for smaller sets, but as I said, for what I want to show you, it's not important, and this will make it much cleaner. Good, so that's the expander. So now let me tell you the lemma. So for every s bigger than 0, let's say, for some reason we said integer, but I know what's the reason, but it's a bit silly. But anyway, and graph G, we can delete up to 4s n log n edges from G and decompose, and all my decompositions are always edge decompositions. So I'm partitioning the edge sets, not the vertex sets. The composition of edges of the remaining edges into G1 to Gn such that each Gi is 1 over 32 log squared size of Gi S expander, robust expander. And their total size isn't too big. Sum of G1 plus sum of G2 plus so on. How many did I say I have? Not n, r is at most 2n. Okay, so yeah.
Yeah, the statement seems a bit weird to me. You're given a decomposition, or are you trying to say that you can decompose the edges into?
We can find it. So we can delete blah, blah, blah edges from G and find, I see I'm missing a verb. Thank you. Yes. Very good. So what it says is you can partition the edge set. So we sacrifice a few edges. I'll get back to that in a moment. But then what we get, the rest of it, most of the graph in some sense, we partition it as edge, like we partition the edge sets into these expanders. So they have a 1 over log squared expansion compared to 1 over log that we worked so far, but another log. And the key thing is actually in total, they don't use too many vertices. So if you think about it, we have n vertices in total. And I'm telling you that as you go over all of these, they should not add up their sizes, their orders should not add up to more than 2n. So if you think about to how many of these expanders a typical vertex belongs to, it's 2. Right? So it's almost a vertex decomposition, but not quite. Like you lose a little bit. And we can make this easily 1 plus little of 1 times n. That will be your exercise. So the 2 here is just for simplicity for the argument. Okay, and so now what else is important to point out here? So because of this, this is not a full decomposition lemma, right? You sacrifice some edges, which we don't really know what happens. So what CS people like to do is then apply another decomposition lemma to that set and keep doing that, and then you get some hierarchy of these things. What we can do just from the basic version of this lemma is just plug in s equals 0. That's legitimate for this lemma, and then you get a full decomposition. Right? If s is 0, I'm not allowing you to delete any edges. I get the full decomposition of everything. But what you lose is robustness. So you just get our 1 over log squared expansion. So in the application, next time, you will see, I hope, both versions applied to the same problem, both the full decomposition and the partial one. So, and also I should say that this lemma has been tweaked, improved, modified in about 4 ways now. So it's quite flexible depending on what you want to do, but you need to know what you want to do. So I don't know a general overarching lemma that gives you everything. So once you want to apply it to a problem, figure out what you want, and then look at the proof. And I'll probably not actually do the proof of it next time, just sketch, and so you can also think about that if you want. So thank you, and see you tomorrow. Or I actually have to.